This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The first lecture, the Bloch Equations and Image Contrast, is broken down into 4 parts. Lecture 1, Part 4, covers the Bloch Equations, Relaxation, and Image Contrast. The learning objectives for this lecture include being able to describe the addition of relaxation to the equation of motion to form the Bloch equations, differentiate between the Bloch equations in the lab and rotating frame, remember a few specific T1 and T2 values, learn which magnetization components are governed by T1 and T2, and understand the importance of free precession with relaxation in the rotating frame and forced precession without relaxation in the rotating frame. And finally, discuss how RF pulses, T1 and T2, confer image contrast. In 1952, the Nobel Prize in Physics was awarded to both Felix Bloch and Ed Purcell for the development of new methods for nuclear magnetic precision measurements and discoveries in connection therewith. Bloch did pivotal work at Stanford from 1934 to 1983, and you can read more about that online. The Bloch equations, of course, are named after him. So we begin by examining the equation of motion for the bulk magnetization, and here see that the Bloch equations adds 2 more terms. The first term confers relaxation dynamics for the 2 transverse components of the magnetization, shown here in the laboratory frame. And a third term confers bulk magnetization relaxation dynamics to the Z component of the magnetization. And we also introduce the term M0, which refers to the equilibrium value of the magnetization when the spin system is at steady state. This is a differential equation. It's an ordinary, coupled, and nonlinear, which makes it exceedingly complex and not possible to solve analytically. So there's no analytic solution in general, but analytic solutions are available for simple cases, some of which we'll examine in this course. And of course, numerical solutions are available for all cases, and Bloch equation simulations become an important component to understanding MR signals and sequences. This expression is actually a phenomenological expression, and while we were able to derive the equation of motion, the exponential behavior that will arise as a consequence of adding the 2 terms related to transverse and longitudinal relaxation are added because they match the apparent phenomena quite well. They cannot be derived from first principles. The Bloch equations, of course, can be rewritten in the rotating frame, and here we see the equation of motion written in the rotating frame, where the bulk magnetization vector is subscripted in the rotational coordinate system. And we use here the effective B field in the rotating frame. And the transformation to include relaxation in the rotating frame is relatively straightforward. Importantly, you'll notice that longitudinal relaxation term looks the same because the k hat and k hat prime coordinate axes are shared between the 2 coordinate systems. Precession is indicated by the magnitude of m, which is unchanged, and it accommodates or accounts for the phase or rotation of the bulk magnetization changes due to the B0 field. So that's this first precessional term here. And relaxation accounts for changes in the bulk magnetization during the return to equilibrium. The T1 changes are relatively slow, and the T1 values are on the order of hundreds of milliseconds, and the T2 changes are faster with relaxation time constants on the order of tens of milliseconds. Interestingly, a concept that we'll develop is that the magnitude of the bulk magnetization can in fact be 0 at certain points in time. And this helps develop some insight to how image contrast can be evoked. The Bloch equations can actually be further expanded to include diffusion terms, a topic that we'll evaluate much later in the course. Spins themselves are thermodynamically driven to exchange position over periods of time, and this leads to diffusion signal consequences. And expanding this Bloch equations to include the diffusion terms is usually referred to as the Bloch-Torrey equations. So here we see a cross-section of an MRI scanner, and we remember the B1 coil on the outside can be used to excite the spins, but the spins in that state, of course, are not preserved, and they'll relax back to their equilibrium state after some period of time. So that was spins. I can show it again. Whoops. We can see the spins here precessing as a consequence of the external B0 field, excited to precess apparently in the transverse plane by the B1 field, but then they relax back to their equilibrium position after some period of time. So T1 and T2 values are tissue specific, and this is what fundamentally makes MR so important from a clinical perspective, the so-called soft tissue contrast. So we can see, for example, that gray matter has a T1 of 925 milliseconds, while white matter has a T1 value of 790 milliseconds. These values are approximate values for 1.5T imaging systems. So as a consequence of the Bloch equations and tissue-specific T1s and T2 values, the bulk magnetization vector is not of constant magnitude. We can manipulate the magnitude of the bulk magnetization through the application of a series of RF pulses and spatially localize that information using gradients. So by manipulating the magnitude of the bulk magnetization, we can generate a wide range of image contrast. So here we see very limited image contrast. This is a proton density weighted image. And by changing the timing here, this is the inversion time after an RF pulse, a concept we'll develop later, we can see that we can actually get dramatic changes in image contrast just by the timing of our imaging experiment relative to the application of an inversion pulse. And allowing the contrast to develop in very different ways as a consequence of the underlying T1s of these different tissues. So let's say a little bit more about T1 and T2 relaxation time constants. The longitudinal T1 refers to the longitudinal or spin lattice relaxation, and it's driven by return to equilibrium. It's typically typical T1 values are tens of milliseconds to maybe hundreds of milliseconds. And T1 weakly increases with increasing B0 field. So there is a small effect owing to moving from, say, a 1.5T scanner to a 3T scanner. The T1 can actually be decreased through the use of a contrast agent, something we'll discuss later in this course. Liquids in particular have long T1s, while fats have relatively short T1s. And it's important to remember that short T1s are bright on T1 weighted images. And this is something that will become more apparent when we develop the mechanics of spin dynamics during relaxation. In comparison, we have T2 relaxation, or so-called transverse or spin-spin relaxation. And this arises through molecular interactions that lead to spin dephasing, that is, spins that point in different directions and lead to signal attenuation. Typical T2 values are on the order of less than tens of milliseconds, although they could be in the couple of hundreds of milliseconds for liquids. T2 marginally increases with B0. It's really relatively constant as a function of B0 for the field strengths that are typically used for clinical imaging systems. T2 can also be decreased with contrast agents, although the effects on image contrast will be quite different between T1 contrast agents and T2 contrast agents. Liquids in particular have long T2s, and solids have especially short T2s. And it's good to remember that T2s are bright on T2 weighted images. Lastly, T2 is always less than T1, and this is helpful for remembering values associated with these time constants and a good principle to keep in mind. So here's a diagram borrowed from Bushberg's book on the essential medical physics, just showing how T1 and T2 changes roughly as a function of molecular motion, molecular size, and molecular interactions. And so we have long T1s rather in some circumstances, and short T1s or T2s in other circumstances. And while these terms may not make intuitive sense for those without a lot of background in molecular dynamics, we can associate these with specific tissue types. And so muscle, for example, has a relatively long T1 and short T2. Fat has a relatively short T1 and a relatively intermediate T2. and CSF has a relatively long T1 and a relatively long T2, and accord with the sort of molecular dynamics that were shown on the previous slide. So let's look at an example of T1 weighted magnetic resonance imaging using inversion recovery. So in this case, we do a thought experiment where all spins for all tissue types would initially be at thermodynamic equilibrium. And if we play an inversion pulse, we can turn the spin system upside down, and they'll now have negative values of the thermodynamic equilibrium magnetization. And that's generally going to be very, very similar values for all tissue types. But now what happens as time evolves is that these tissues will track on different exponential curves depending on their fundamental T1 relaxation time constants. And the goal of imaging is to get a snapshot or a picture of the bulk magnetization dynamics at a particular time. And if we look at an early time here, there's very little difference in the available magnetization for different tissue types. And if we take a snapshot picture here, the bulk magnetization vectors will be similar and the image contrast will be quite flat. Now, something to remember, and it's a concept we'll have to develop more in later lectures, is that when we look at images, we're fundamentally looking at magnitude images. And so any so-called negative magnetization has had the absolute value taken or its magnitude extracted. And so the relaxation time curves actually follow these somewhat more complicated absolute value curves. So here we can look at what happens to the image contrast if we wait a slightly longer amount of time after this inversion pulse. And we can see, for example, that at this point, the white matter signal is tracking below the gray matter signal, and the white matter signal will appear a little bit darker than the gray matter signal. If we wait till a later point in time, say here, for example, then the white matter has effectively been nulled. It's crossing through the so-called 0 point. So the bulk magnetization vectors for white matter are very, very, very low. But the gray matter bulk magnetization is still notably non-zero, which gives dramatic contrast between white matter and gray matter. And if we wait until a much later time, as shown here, then the gray matter signal is actually lower than the white matter signal, and this gives relatively inverted contrast compared to, say, the second image that we were showing before. So again, MR is well regarded for having dramatic soft tissue contrast and the ability to manipulate widely the soft tissue contrast as a function of RF pulse timing, as a simple example. Here's a different example. This is a so-called T2 weighted image. And so here we can get a snapshot of the transverse magnetization at different time points. So you can picture tipping the magnetization into the transverse plane and then taking pictures after different intervals. Those intervals actually correspond to what's called the echo time. So we have very, very short echo times all the way to quite long echo times. And because the T2s of these tissues are quite different, the T2 of white matter and gray matter are relatively short or intermediate at about 100 milliseconds, but T2 has a substantially longer value for cerebrospinal fluid. And so in this dramatic example, we can see that in fact we do generate some white matter, gray matter contrast as a function of longer echo times, more T2 weighting. And if we wait till extremely long times, then we essentially accentuate the CSF signal only while suppressing largely the the white matter, gray matter signal, owing to the fact that signal has decayed so substantially relative to its relaxation time constant. And so this is a nice example and a reminder that long T2 is bright on a T2 weighted image. And a T2 weighted image generally accords with having a long TE, a long or intermediate TE. So let's think about free precession in the rotating frame again, but in this case, we're going to add back in relaxation. So we begin with the Bloch equations that were shown earlier and need now describe the B effective field that will be used under these circumstances. And so remember the general definition of the B effective field includes a fictitious field plus the applied B field described in the rotating frame. Here, the fictitious field just accords with the externally applied B0 field for a conventional MRI system. And we need to define the B rotational field here, again, for free precession in the rotating frame. And we know that the applied B0 field in the rotating frame is just B0 K hat. And so, as we recall previously, we still have that the B effective field is 0. There's no effective B field for free precession in the rotating frame. So here, if we look at free precession of the rotating frame with relaxation, then we see that we just have two terms that become necessary, both the relaxation terms. So there's no precessional term. We still have the T1 and T2 relaxation terms. We'll drop the diffusion term so as not to further complicate things at this point. And we end up with a system of first-order, linear, separal ordinary differential equations that are homogeneous in x and y and inhomogeneous in z. So that's what this system of equations actually looks like. If we expand out the cross products, we can see that we have a system of three different differential equations for which we can derive the following solutions relatively easily. This is an uncoupled inhomogeneous differential equation, and this is an uncoupled inhomogeneous differential equation. The first two equations here rather are inhomogeneous. So free precession in the rotating frame with relaxation is really important. We use these equations all the time because they describe the relaxation of the magnetization during intervals when RF pulses are not being applied and give us a little bit more intuitive insight because we're working in the rotating frame. And so we'll use these expressions frequently to understand image contrast and signal dynamics in magnetic resonance imaging. And what they basically say is that the X component and the Y component of the transverse magnetization will simply decay as a function of T2 and time relative to the initial conditions, the initial amount of transverse magnetization available. The MZ magnetization undergoes a different kind of dynamics, and it shows that there's a return to equilibrium term on the front end here. So as time elapses, the MZ component becomes increasingly closer and closer to the M naught equilibrium value, and any so-called prepared magnetization along the Z-axis actually decays as a function of time. Anything perturbed by RF pulses is away from equilibrium, and so those magnetization components will decay. So what about forced precession in the rotating frame with relaxation? So if we examine a forced precession in the rotating frame with relaxation, we again need to look at our Bloch equations in the rotating frame and think about what's our B effective. We expand our B effective for a conventional MR system, defining the so-called fictitious field just to accord with the conventional B0 field. But now we need to use a different rotational externally applied B field here. And so it's the combination now of the externally applied B0 field plus the forced precessional term in the rotating frame. So we have both of these fields being applied physically, and these are offset by this fictitious field, which gives rise again to the B effective field. So the composite B effective field at this point just looks like the forced precessional terms here, the envelope function, and then two components projected onto the X and Y axes. And this is the effective B field for forced precession in the rotating frame. So we can use that forced precessional terms into our Bloch equations again. We can write out this cross product term, filling in for the two forced precessional terms. We don't have a Z term, and we still have the two relaxation terms. If we carry out this cross product and add together the terms on the right-hand side here, we get a system of differential equations. This system is first order, linear, coupled, inhomogeneous, and analytic solutions are not possible, but numerical methods, of course, can be used. So we can see that there's coupling here between, say, the X and Z components, the Y and Z components, and for the Z component, it couples to both X and Y, and of course, the relaxation components make things more complicated. So we've considered free precession, forced precession, we've considered the lab and the rotating frame, we've talked about relaxation, and we've considered all of these combinations, at least briefly, for which there's a total of 8 different circumstances. Which ones really concern us in Rad229 the most? The first is free precession in the rotating frame with relaxation. We want to account for the return to equilibrium during intervals when RF pulses are not being applied. We also care a lot about so-called forced precession in the rotating frame, but because forced precession is a short duration event relative to the time constants, T1 and T2, we don't need to always account for the effects of relaxation, especially when trying to work towards analytic solutions and a more intuitive understanding of what's happening. And importantly, you'll note that we principally care about describing bulk magnetization dynamics in the rotating frame. So we can, in fact, simulate all of them, but as the expressions have demonstrated, some of these are relatively complicated and better left to simulation. So what about K-space and imaging? This is something that you'll have to turn to Lecture 2 to learn more about. You can click the links below and join us for those lectures. All right, thank you.